All right. Today I am going to, similar to the series of Black Scholes videos I did, I'm going to do the Garman Kohlhagen model of an exchange rate option, a foreign exchange option. Unlike Black Scholes, where there's tons of videos online already, at least on YouTube. There don't seem to be as many or any really taking the Garman Kohlhagen from start to finish. I mean, assuming I'm searching for the right thing. So I thought that maybe this could help somebody. And also, luckily, I have a new pen system this time, so hopefully that'll go a lot cleaner. I'm going to do this in the same way I did the Black Scholes videos, that is 4 parts, just to be very thorough again. So this first video will be deriving the PDE. The second will be talking about changing measure. The third will be solving a couple of SDEs that we'll need for the solution, which will then finally come in part 4. And I'll do that via Feynman Kac, to again kind of show the beauty of that method. Anyways, let's get started here deriving the PDE. So in the Garman Kohlhagen model, it's basically a modified Black Scholes model. So again, we're basically going to consider a contingent claim, some payoff function phi that's based on the exchange rate at time capital T, and then we're going to say we have a pricing function f, which depends on time and the exchange rate at time t, and we're going to say that this, for shorthand, is equal to pi at t, and a lot of times I'll just simply write pi just for simplicity. And we also need then, importantly, x is an exchange rate, and importantly, it's domestic to foreign. So we also need then assumptions for the dynamics of a couple things. As should be obvious, we first need an assumption for the dynamics of the underlying, which in this case, again, is this domestic to foreign exchange rate. So that is going to be modeled by our old friend, the geometric Brownian motion. Plus sigma x. So here alpha is sort of the P drift of the exchange rate, and sigma is the volatility, the diffusion coefficient of the exchange rate. Now, when I first saw this, I really disliked the idea of modeling an exchange rate with a geometric growth process, given that exchange rates are, known to be mean reverting and extremely difficult to forecast. And you'll see in the end that the way that it ends up working out in the end, it's not that bad, and it actually has somewhat of an economic interpretation. And also, don't forget that, first of all, we have a fixed time here, and we're under the probability measure P, so, it's reasonable to think that, maybe you or, whoever's looking at this would have a P expectation for the drift of the exchange rate, at least from time little t to big T, or again, if you're of mind that rates are mean reverting and hard to forecast, you also could simply make alpha equal to 0, and then you would just have say a flat noise process. But I still don't like it. But again, for the moment, don't look too much into the the perceived problems with modeling and exchange rates with the geometric growth process. Under Garman Kohlhagen, their big sort of development is that we are going to deal with two different interest rates. So you have a foreign bank account, so I'm going to denote that with a superscript F, and then also a superscript on the rate. So just like in Black Scholes, where we just modeled a single bank account and we had dB equals R BDT, so it's the same kind of idea. Again, this time though, we need two bank accounts. That's the foreign bank account, and then we'll have a domestic bank account where we just change the superscripts. Okay, so these are sort of the basic three dynamics that we start out with. So you have the underlying rate, the foreign bank account, and the domestic bank account. Now, importantly, we need to take one more step. In the Garman Kohlhagen model, we need things expressed always in domestic currency. So this, right in this form, is a bit of an issue. We can't work with this. We need to translate this into domestic currency. So how can we do that? Well, it's not that bad. All we simply do is we create a new process that I'm going to call B tilde F, and that's simply equal to the exchange rate times the foreign bank account. So that'll get us into domestic currency. Now, we obviously, need the differential of this. So let's figure that out. Now, if we recall the Ito product rule, which basically says that if we have, say, dxy, that's going to be equal to dx times y plus dy times x plus dx dy. So translating this into the problem of trying to figure out the differential of b tilde, we're going to have that d b tilde is equal to x db tilde, sorry, it's not tilde, just bf plus bf dx plus dx dbf. All right. Now, obviously, we know both dx and dbf because we define them up here. So let's go ahead and fill these things in. So we're going to get that d b tilde f. I tend to be sloppy with my f's, by the way, so if you ever see something in the superscript here that looks kind of like, that or even worse, just know that it's an f. I hope that at least it's differentiable from a d, so if you ever see anything weird, just assume that's an f. So d b tilde f then is going to be equal to x times r. So now I'm filling in d bf dt plus bf, and now I'm going to fill in dx alpha x t dt plus sigma x t dwt, and then we need this cross term. It's going to be plus rf bft dt times alpha x t dt plus sigma x t dwt. Now let's take a look at this term. So the Ito multiplication rules, I talked about this in my last series too, that basically any dt squared terms are basically 0, they cancel. Any cross terms, so dt times dw or dw dt terms, are also 0. The only thing that will remain is if you have a dw squared term, that's going to become dt. So the point here is that we see here we have none of these dw squared terms, so this entire thing is just going to cancel. So in the end, after gathering like terms and simplifying out of just this part, we're going to finally be left with, that d b tilde f is going to be equal to, I'll do this in two parts just to make it very clear. It's going to be x bft times alpha plus rf dt plus sigma x bf. You could have a t dependence in these x's too. I for some reason dropped that, but whatever. bwt, now recall that we define this as the b tilde process itself, so I'm finally going to rewrite this as d b tilde f is equal to b tilde f times alpha plus rf dt plus sigma b tilde f t dw t. Alright, so that's another important differential process that we need. So let me rewrite everything down here just to really make it succinct. So we have this is the foreign bank account, the differential of the foreign bank account in domestic currency. Remember, we also had the dynamics of the exchange rate as under P as alpha x dt plus sigma x wt. Then we had the raw foreign bank account, and then the raw domestic bank account. Sorry about that. Alright, so these are all the important dynamics that we need to get going. So, foreign bank account in domestic, underlying process, foreign bank account in foreign, domestic bank account in domestic. Alright, so let's now move on to thinking about a value or a wealth process. Basically a portfolio that's made up of the underlying and the claim or option itself. So we will have dv, so that's our value process, or you can think of it like a portfolio, is going to be equal to, so the change in the value process is equal to, we can write it as the value process times the weight of the underlying times the differential of that foreign account in domestic currency. So that's like a percentage change in that foreign account in domestic, plus the weight of our claim times the basically percentage change in the claim. Now, if you need to stop and convince yourself that this works, go ahead. I derived this in a few more parts, I think in like 3 parts in the first video of my Black Scholes series. So you could go back to that too. But for now, just trust that this idea makes sense. So with that, we're going to move on to something slightly different. So apply Ito now to f. So remember, we assume that we had this pricing function, f of txt. So apply Ito's lemma to that. I mean, you're not... I say apply Ito's lemma. Basically, it's almost asking for Ito's lemma. So we'll have df is equal to f. And I'm going to use here subscripts to denote partial derivatives. So this is, you know, partial f over partial t. As you can see, I have a bad, my partial derivatives tend to look far too much like 2's, and also I got in the habit of the subscript derivatives, because for me they're easier to type in LaTeX. So for here, subscript denotes partial derivative with respect to t. So Ito's lemma, ft dt plus partial to x dx plus 1/2 second partial to x dx squared. So again, I said, you know, apply, I should say Ito, but, you know, it basically just simply is Ito's lemma. So let's fill in. Obviously, we know these dx's. It's part of our assumption. So let's fill those in. So we'll have that df is equal to partial to t dt, so that doesn't change, but then we're going to have the partial with respect to x times alpha x t dt plus sigma x t dwt, and then plus 1/2 second partial to x. And I'm going to save the time in you know, squaring this. We just talked about the Ito multiplication rule. So if you think about foiling this term, again, remember the dt squared and the cross terms drop out, so you're going to end up just with this final term squared. So I'll just go ahead and do that right now. So it's very obviously just sigma squared x squared, and then again the dwt, when you square it, it becomes a dt. So let's gather like terms. So we have that df is equal to ft plus f x, and then we'll have, nope, sorry about that, alpha plus 1/2 f x sigma squared x squared, we can say that dt plus, and then we have sigma x t dwt. Now here we're going to do a little trick. We're going to multiply and divide everything by f. So we're going to have f times this term over f, and then f. I say everything, but you know, and then cut off the division here. That is, don't divide the dt and the dwt by f. And what we're going to do with this is we're going to call this alpha subscript f, and this is going to be sigma subscript f. Now here, I know this could be a little confusing, but it's just the way that I like to do it. Here the subscripts aren't denoting partial derivatives. They're simply just a subscript to differentiate this alpha and this sigma from the the alpha and the sigma of the underlying foreign exchange rate. All right, so why do that? Well, let's simplify this, giving these new terms we've created. So we have df is equal to f alpha subscript f dt plus f sigma subscript f dwt. Now, if you remember in the beginning, we said assume, or we just, f is our pricing function, and we said think of that as pi. We assume the pricing function satisfies pi. So filling in the f's with pi, and then dividing everything by pi, we can then say that the pi over pi equals alpha subscript f dt plus sigma subscript f dwt. Now why? What's the point of getting this term? Well, if you recall, it's part of our value process. So, this is nice. I mean, we have this. I mean, we don't have it fully, but, we have everything we need for it, given that we already figured out the differential of the b tilde process. We just figured out d pi over pi. So, let's go now and start filling those in. First, I'm going to do a little ancillary calc of that d, just to make this a little bit cleaner. I'm going to do this so it's this part here. I'm going to do this separately first. So let's see what we'd have there. We'd have, let's just write the process, b tilde f. It was alpha plus r f dt plus sigma b tilde f t, and that's over the process itself, so these cancel out. So you see that we're just left with alpha plus rd f dt plus sigma dwt. All right, so let's get these into the wealth process now. So this, let me just write this down here just to make it so you don't have to keep pausing or jumping back the video. So again, we had dv equals v times the weight in the underlying db tilde f b tilde f plus. All right, now filling in this and this, we're going to get that dv is equal to, and again, I could have, t dependences here, but I'm trying to save a little room, equals v times weight in the underlying times alpha plus r f dt plus sigma dwt plus the weight of the claim times alpha subscript f dt plus sigma subscript f dwt. All right. And let's simplify this a little bit and gather like terms. So our dt's and our dwt's. So we're going to have that dv is equal to v times the weight, the underlying, alpha plus rf plus weight of the claim, alpha subscript f, dt plus, so I kind of split this up in, you know, the v's. Weight of the underlying times volatility of the underlying plus the weight of the claim times sigma subscript f dwt. Alright, so why is it important to get it in this form? Well, now we need to bring in some option pricing theory. So here we have a drift term, right? We have some term attached to dt. Well, we know that this should be equal to the domestic risk-free rate, y, for no arbitrage. Furthermore, we have, not confuse that there, we have this term attached to the Wiener process. What should this be? This should be equal to 0. Why? We're trying to form the portfolio with no risk. So the whole point of this is to form a riskless portfolio that therefore by no arbitrage earns the risk-free domestic rate. So the whole point of doing this was that we can now cast this as a system of equations. So we're going to say that Wx, so this is this blue one up here, D. Now for the yellow one, sigma f equals 0, and then we need one more. What is it? Well, the weights should sum up to 1. So here's our system of equations. This first one is going to lead to the PDE, so we'll do these two first. Let's see, should I do these or should I just give the results? I'll just do it. So I'll do this step by step, but I'll go quick. I also did this in the first Black Scholes video. If you want, I think, a slower rendition, but let's just do this real quick so we can say that. So I'm starting with the third equation now. Quickly say down 1 minus w pi. So now I can plug that into equation 2 and get 1 minus w pi sigma plus w pi sigma subscript f equals 0. That's the same thing as saying that. So now I'm just bringing this in. Sigma minus w pi sigma plus w pi sigma subscript f is equal to 0, which is the same thing as w pi sigma f minus sigma. So now I'm combining these and factoring, and then moving this to the other side equals negative sigma. So that's the same thing as saying that w pi equals negative sigma over sigma f minus sigma. I don't like the negative in the numerator, so therefore I'll say that w pi is equal to sigma. Alright, so that is the first important result there. So that's the weight of the claim. Now let's figure out the weight of x. So this is done by then going back to equation 3. So we'll get wx plus, and then we're going to fill that in. sigma over sigma minus sigma f. And again, the assumption is that the weight should equal to 1, so that's the same thing as saying that Wx is equal to 1 minus sigma over sigma minus sigma f. So I'll turn this into a common denominator with this to get that Wx equals sigma minus sigma f over sigma minus sigma f minus sigma over sigma minus sigma f. So these will cancel and you'll get that Wx is equal to negative sigma subscript f over sigma minus sigma f. And again, I can get rid of the negative in the numerator to just have that Wx is equal to sigma subscript f over sigma subscript f minus sigma. All right, so working these two equations, that's what we find for w pi and Wx. Now again, what we'll do is put these into equation 1, which will again lead us to the PDE. Just to have them both up here for you, I'm going to rewrite that there. All right, so we're going to put those into equation 1. So we'll have sigma subscript f over sigma subscript f minus sigma alpha plus rf. And then it was plus, you know what, you can see here I would basically be adding this term now. I want to immediately get it into a common denominator, so I'm going to instead subtract, so I can get minus sigma over sigma subscript f minus sigma instead. So that's, this part. And then alpha f equals the domestic rate. So that just makes it so that, these two then are the same. Which allows then to quickly move to sigma subscript f times alpha plus rf minus sigma alpha subscript f is equal to sigma subscript f rd minus sigma rd. So I multiplied through by these denominators and then also expanded. Let's see here, so yep, now I'll move things around to collect like sigma and sigma f terms. So in doing that, we'll get that sigma subscript f alpha plus rf minus rd is equal to sigma times alpha subscript f minus rd. And then finally, so divide each, by these. So finally you'll get that alpha plus rf minus rd over sigma is equal to alpha f minus rd over sigma subscript f. So here you have sort of a market price of risk equivalency between the underlying and the claim. Now what we'll do here is let's call this one lambda. So that would leave us with lambda equals alpha subscript f minus rd over sigma subscript f, which is, so multiplying through by sigma subscript f, we just have lambda sigma subscript f equals alpha subscript f minus rd. All right, let's move forward with this equation. Now, in moving forward, we know what sigma subscript f and alpha subscript f are, right? We defined them when we did our little, we looked at our value process and then did our little trick of multiplying and dividing by f, and then decided to define these two terms by alpha subscript f and sigma subscript f. So we know what these are. But just to make it clear, I'll rewrite them here. So sigma subscript f was equal to partial to x sigma x t over f, and alpha subscript f was partial to t plus partial to x alpha x t plus 1/2 second partial to x sigma squared x squared over f2. Let me just double check that. Yes, looks good. All right, so let's plug these in to this equation. So we will get lambda times partial to, so yeah, so here's where I said please don't be confused. Here the f subscripts are simply f subscripts, but anything t or x is denoting a actual partial derivative. So lambda times partial derivative of f with respect to x times sigma xt over f is equal to partial with respect to t. After this step, these are gone, so you don't got to worry about that confusion anymore, but partial f with respect to x, alpha x t plus 1/2 second partial with respect to x, sigma squared x squared t over f minus r d. Alright, so now I'm going to move this term to the side and then multiply through by f. So we'll get f, so first partial with respect to t plus partial to x, alpha x t. So then it's going to be minus f, bring that in closer, don't want to run out of room, minus sec to x lambda sigma plus 1/2 second partial to x and then minus rdf, because remember we multiplied through by f, and then that's going to equal 0 since we moved everything to one side. Okay, let's combine these terms, so we'll get f to t plus first to x alpha minus lambda sigma x plus 1/2 second partial to x sigma squared x squared t. Okay, now we know lambda, don't we? Yes, we defined it up here. We said have it equal to this MPR. So let's plug that in. I'll write it down here. Okay, let's plug that in. So I'll just do this term just to keep it clean. So we have alpha minus alpha plus rf minus rd over sigma times sigma. These will cancel, these will cancel. This will become a negative, that'll become a positive. So we'll simply have rd minus rf. All right, so let's finally write this. So finally we have first derivative with respect to t plus first derivative to x, rd minus rf is t plus 1 half second partial to x sigma squared x squared minus rdf equals 0. And of course we'd also have a terminal that at maturity it would satisfy our payoff function. So there you have it. This is the PDE for the Garman Kohlhagen foreign exchange model. And as you can see now under Q, our drift has changed to the domestic rate minus the foreign rate. So, you know, slightly better intuition here now. It sort of has a Mundell-Fleming-ish or, you know, carry trade type interpretation that, first of all, none of this matters in terms of the theory of pricing the option. It's just nice when something sort of makes sense intuitively. So you can think of it like, okay, if the domestic rate is yielding more than the foreign rate, that'll attract capital flows, and therefore the domestic foreign exchange rate should be expected to appreciate. Likewise, if it's the foreign rate that's higher, then that should attract capital flows, and therefore the drift of the rate will be negative. But again, that doesn't really matter. It's just nice to have a more intuitive interpretation than simply an exchange rate's going to follow some, you know, some P geometric growth process, which doesn't seem that intuitive for an exchange rate. But in any case, that's the PDE. So again, the next video I'm going to show you how change of measures work in this framework. So basically we know by this that what we're going to find, the first thing I'll do is I'll prove that when changing from P to QD, that we're going to have that the differential of x is equal to RD minus RF. Q, and then I'll denote it D, you know, to match this. But then importantly, for the eventual solution, I'll also show you then how to move from QD to QF, and then get something, and then, you know, DWQF. That'll be important for the solution. And then the third video, I'm going to show you how to solve. So for the solution, we'll also need to then solve these two differentials. So the solution to those, and then the final video again will be deriving the actual solution to this. And if you know it, so a European call, the exchange rate, I think it comes to the rate now time discounted at the foreign rate times n of some d1 minus the strike discounted at the domestic rate times some n of d2. I think that's right, but we're going to then actually derive this step by step using the Feynman Kac theorem.